I'm going to use their interactive graph to talk about continuity on an interval. It's pretty good. If you're talking about an interval that is open-ended on both ends, then it is continuous on that open interval, but not at the endpoints. Likewise, if you are open-ended on one end, then it won't be continuous at that particular point, but it will be continuous at the point if it is inclusive to the function. Same way on either the left or the right, and similarly if it's inclusive on both ends, then it is continuous over that entire interval, including the endpoints. If I want to consider why this might be true, I can just think about the limits from the left and the limits from the right, and note that if it's open-ended, then at that open ending, the function value and the limit will not be the same, so therefore it couldn't be continuous on those open endpoints. Next, I'm going to be looking at example 5, and they would like for me to determine the intervals of continuity. If I look at this in individual pieces, I see that the left-hand piece is continuous from -infinity up to 0 and including that point. If I look at just the right-hand point, and I'm just looking at these, the right-hand section, and I'm just looking at these in sections, if I look at that left-hand section, I see that it is continuous, not at 0, but all the way up to infinity. Now, if I want to discuss the entire function, which of course I do, I see that the limit at x equals 0 does not exist because the left and the right hand limits are not the same. Therefore, I can say that the function is continuous only from -infinity up to 0, not including that point, even though that left-hand section might have been continuous at that point 0, the entire function would not be continuous at that point. Next, we're going to look at continuity of roots. What we're going to do first is we're going to explain the even one, since that's our example first. So we have an even root because this is basically to the 1/2 power. So your n in this case would be 1 and m would be 2. And it says it's continuous at all points A at which f is continuous. Therefore, this will be done in parts. I can see that my function is continuous all throughout this 9 minus, because my f of x, let's just look at this first. My f of x in this case is 9 minus x squared. And the domain of this g of x, the domain itself, would be -3 to 3, and I need to see if it's continuous all throughout that realm or not. Now, I know that it's continuous from open interval -3 to 3 by virtue of that theorem 2.12. So it's continuous from -3 to 3 because it only guarantees me that it's continuous as long as the function itself is greater than 0, and obviously it's equal to 0 at those endpoints. So I need to see if I include those endpoints, is it going to be continuous, and does that exist? So my left-hand limit, so let's just look at the limit as x approaches -3 from the right of this f of x. That would equal that point -3, which is also equal to that, I'm sorry, -3 should be a 0, that y value is 0. Thinking -3 because it's f of -3, sorry. So it would equal that function value, so I have continuity on that left-hand side, and I would do something similar on the right-hand side. Therefore, it would imply that it is continuous on -3 to 3. Now, if I want to formally state that, I also have to go through the limit as x goes to 3 from the left of f of x also equals 0, and that is f of 3. So now I can say that it is continuous along that entire interval, including the endpoints. And those endpoints will get you messed up, especially on a multiple choice question. On this next example, I have as my inside function this x squared minus 2x plus 4, and that's a polynomial function, and I know that that is continuous on its entire domain. My m in this case is 3, so m is odd, so I'm looking at this top portion of the theorem. If m is an odd integer, then my entire function is continuous at all points at which f of x is continuous. Since it's continuous on this polynomial, it is continuous on the entire domain due to the fact that there's a polynomial on the inside function and the odd root, of course. Inverse functions, if the main function was continuous, by virtue of the fact that in order to have an inverse it has to be a one-to-one function, because of that fact, then the inverse function would also be continuous. Therefore, when I look at the following transcendental functions, both the function and their inverse would also be continuous. So let's do some examples. I can't get this one directly, but I can use, well, first I think I'll factor. I see a little trig work here. So this would be just a difference of squares. Ka-chunk, ka-chunk. All right. Limit as x goes to 0 of cosine x plus 1. I can use my sum laws for limits. Limit as x goes to 0 cosine x plus the limit as x goes to 0 of the constant function 1. I can do direct substitution at this point because I know the limit of the cosine x as x approaches 0. I've looked at that one earlier, so that would be a 1 plus a 1. This equals 2. So the limit of this first function is 2. Let's look at this next one. I'm going to use those same sum and difference laws. So I've got 4th root of the natural log of x. That's fixing my natural log here. Natural log of x plus the limit as x goes to 1 of tangent minus 1 of x. Oh, I found the limit of the first one, but I didn't discuss the continuity. So this would be my place of discontinuity at 0, and since the limit exists, which would be the function value, then the first one would be continuous. I do need to follow those same little criteria that I've been following. So let's look at this next one. Now the natural log function is, I'm looking at the inside and I'm doing the rooted power. This is an even function. I see that, number one, natural log isn't defined for negative numbers or 0. So this guy right here, this section, I can say the natural log at 1 would be, alright, I thought it best get a little natural log graph up here. So it is continuous. The natural log is actually continuous from 0 on up to infinity, not including that endpoint. So natural log would be continuous from 0 to infinity. However, it's underneath the 4th root. So then that would exclude all of these points. So this guy would be at 1. The limit is going to then indeed be that function value. So I've got from my criteria from the previous theorem on roots that that thing is continuous from 1 to infinity, and then by substituting in to show that it would equal that function value, I can say that it is continuous on this realm. Now the inverse tangent, his domain, the inverse tangent is actually continuous on all negative infinity to infinity, but seeing as this function is a combination of that, it can't be continuous, negative infinity to infinity. Alright, so the combination of this then would be continuous on 1 to infinity. Now I also need to do the limit here. The limit, they've asked me for the limit as x approaches 1. That means the limit from the left must equal the limit from the right. However, I don't even have any function from the left, so this limit does not exist due to the fact that the limit as x approaches 1 from the left of that f of x does not exist. The intermediate value theorem is important because it's used in many different proofs to show that something is true or not true. What it says is that you have a function f and he's continuous, so let's just draw a function f, and he's continuous from a to b, and it doesn't really matter what the function looks like just as long as he's continuous. Let's say here's a and here's b. The intermediate value theorem says if he's continuous on this closed interval and there is some number strictly in between this a and b, so let's say this is right here, this is f of a, and I need to make this a little taller, let's do it like this, and then this one would be f of b, then there's going to be some number in between right here, some number L in between there that will satisfy, there's going to be at least one number in between that will satisfy there's going to exist some x where this happens. So they call it C, it doesn't really matter what it is. And what it kind of means to me is if you were at one point 4'11" and now you're 5'10", there had to be some point where you were 5'4". You might have never measured yourself to be 5'4". Or if you have a plant, and let's say this little flower, and then he was a little sprout at one time. Let's say right here he is 12 inches tall, and right here he was 1 inch tall. At some point, as he was growing, he was 6 inches tall. He was some L that was 6 inches tall, and there was some time associated with that. So in other words, you can't get from point A to point B and their associated y values without going through something that's in between them. Intermediate value theorem. Okay, we're going to use the intermediate value theorem for this particular problem. They've given me a scenario. Here's my function. I'm supposed to have 1,400 in the account after 5 years, and I'm supposed to figure out what would that interest rate be in order to get that 1,400 in that account. So they've told me that there's some interest rate in between 0 and 8% that'll get it for me, and I'm supposed to figure out what that interest rate is. So if down here, this is my A point, A equals 0, and my B point equal 0.08, I'm supposed to find this C value such that I get 1,400 as my L. So first off, let's go ahead and state A equals 0, B equals 0.08. F of A, just chunk that in, would be plug in a 0 for my R. You would get 1,000. F of B, plug in a 0.08. This one isn't quite as quite as easy. Plus 0.08 over 12, all raised to the 60th power. If you crunch these numbers, you should get 1489.85. So I can see that there is going to be some value for my interest rate in between that's going to get it for me. It'll probably be closer to 0.08, as I can tell from this number here. I'm looking for something that is 1,400. Let me write a 1,400 in a different color. So in between this 1,000 and 1,500, there is going to be some interest rate that'll get me the 1,400. So the intermediate value theorem, first off, I have to state that this function is a continuous function. So since A of R is continuous on 0 to 0.08, then we know, seeing as we have found f of A and f of B, that we can write it as 1,000 is in between, and 1,400 is in between 1,000 and the 14,895.85, which is A sub 0, A sub 0.08. Therefore, by the intermediate value theorem, there exists some value of C. Then they ask me to use the graphing utility in order to get that interest rate, and we can do that. If I use their graphing utility, it's really nice because they have the points clearly marked. So I would say for that last part of B, that interest rate is 6.75%. Okay, and that's that one. If you're having any trouble with these, just be sure and attend the Blackboard Collaborate or email me.